accurate sundials made in the medieval world. And equally exciting for me is the fact that it was made by one of the Islamic astronomers who had so heavily influenced Copernicus, Ibn Shatir.
Let's see.
Officials in the mosque claim that the sundial was removed in the 19th century, but Ream's research suggests that an exact replica might still exist, high in one of the minarets, hidden from view. It's not quite the lost Ark of the Covenant, but the idea of discovering a 150-year-old artifact is still quite something. Would you recognise anything if you had a look?
I need to look at the other one. No.
No, it's further on.
Yeah.
Okay. Marking time accurately is essential to Islam. The Quran requires the faithful to pray 5 times a day at 5 very precise times. At the exact moment of dawn, when the sun is overhead, in the afternoon, at sunset, and then again at the moment of nightfall. So for early Islam, an accurate sundial was an extremely important fixture in many mosques.
That's it, I found it! I found it! Yeah. Oh, it's like, here it is, right. That's it, look! Just as described in the book.
It's hidden by the pillar.
Yeah, no wonder they didn't know that it exists here. It's all covered with the pigeons.
Pigeon crap?
Yeah.
Oh.
Oh, great, thank you.
Try that.
So, let's see. Now, this consists of 3 sundials. The main big one, and there's the northern one and the southern one. There is a line here for Salat al-Dhuhr, the midday prayer, and there is one for the afternoon prayer.
Ibn Shatir had calculated the arrangement of these lines so that the sundial remains accurate all through the year, even though the length of the days change.
They will have the timekeeper. It's a very important job.
So he would sit here watching the shadow,
yes, exactly.
And exactly the precise moment for prayer, he'd signal to the muezzin to start the call for prayer.
Exactly.
Okay.
Ibn Shatir's sundial, accurate to within minutes, really showed me how Islam required its scholars to make meticulously accurate observations of heavenly bodies. And I began to understand why Copernicus was so impressed by the work of his Islamic predecessors. They really brought standards of accuracy and precision to astronomy that were unheard of before. They'd calculated the size of the Earth to within 1% and created trigonometric tables accurate to 3 decimal places. And when I met up with Reem Turkmani again on Mount Qasyun outside Damascus, I was to hear about the Islamic astronomer who personified accurate observation. The man whose astronomical tables and measurements Copernicus explicitly makes reference to. Al-Battani. Born in 858 in southern Turkey, Al-Battani made accurate astronomical measurement a personal obsession.
The story goes is that Al-Battani used to observe on this mountain here, in this observatory.
Over 40 years, from 877, both here and in the town of Raqqa, Al-Battani's great project was to work out as accurately as possible the length of the year.
This is a copy of the original manuscript.
Okay.
So I'll show you the chapter at which he explained the length of the year. Okay? The chapter 27. So he first started by citing the ancient values of the Egyptians and the Babylonians, right? And he gives the length of year.
Their estimate of the year was 365 days, 6 hours, and just over 10 minutes. To improve on this, al-Battani used his ingenuity and a device like this, an armillary sphere. He used it to measure how the length of shadows varied over the course of a year. With this information, he was able to work out the precise day on which it's both light and dark for exactly the same time, the so-called equinox. And he repeated his measurements over the course of 40 years. Now here's the clever bit. He examined a Greek text that was written 700 years earlier and discovered the precise day on which its author had also measured the equinox. He now had two vital pieces of data: the number of days between the two observations and the number of years. He divided the first number by the second to arrive at an astonishing result. A year is 365 days, 5 hours, 46 minutes, and 24 seconds.
He gets the new number, which was only 2 minutes off the modern observations.
2 minutes?
2 minutes
so
of only.
The length of a year to an accuracy of just 2 minutes.
Exactly, the one he calculated.
What's astonishing about the accuracy of al-Battani's measurements is that he had no telescope. He used an armillary arm, his naked eye, and devices like this, an astrolabe.
So you move the pointer and you move this disc with it to point towards the North Star. Then these small pointers here, they will give you the location of the rest of the stars and the planets. Okay.
Despite this, among his many other observations is an incredibly accurate figure for the Earth's tilt of just under 24 degrees, about half a degree from the figure we now know it to be. And he didn't stop there. He measured variations in the diameter of the sun to such accuracy that it led him to an astonishing conclusion. This distance, the furthest point the sun reaches from the Earth during the year, known as the apogee, actually changes from one year to another. Also, his tables showing the position of the sun and the moon, which is what Copernicus refers to some 600 years later, set a new standard in precision and accuracy. So al-Battani and his fellow Islamic astronomers were clearly good observers. But so what, you might ask? Well, the answer is that their observations began to suggest to them that the prevailing Greek theory that described how everything in the heavens revolved around the Earth had some serious flaws. This Greek tradition, which had been unquestioned for over 700 years, was based primarily on the work of one of the greatest astronomers of the ancient world.
Claudius Ptolemaeus, or Ptolemy, was a Greek astronomer based in Alexandria in the 2nd century AD. He wrote one of the greatest texts in astronomy, the Almagest, which was basically a distillation of all Greek knowledge on the celestial world. Ptolemy believed that the sun, the moon, the planets and the stars all sat on crystal spheres that rotated around the Earth. So the moon sits on the innermost sphere, followed by the sun and the planets, and finally a patchwork of stars on the outermost sphere. So we human beings sit at the very center of the universe, with the rest of the universe rotating around us.
But as Ptolemy himself realized, there's a problem with trying to describe the heavens as a place of mathematically idealized perfect spheres. And that is that the planets don't really play ball. As they move across the night sky, they change speed, appear to get bigger and smaller, and even go back on themselves. Ptolemy tried to explain this away by arguing that the planets sat on small spheres called epicycles, which rotated around a bigger sphere called a deferent. This explained why they might look as though they were changing size, and why they sometimes even change direction. Unfortunately, that still didn't fit all the facts. it didn't easily explain why the planets appear to speed up and slow down.